Okay, I'm recording now. All right, so we'll have some time. Jeez. All right, I'm sorry about that. We're talking about trees. We had just heard that if you're doing a binary search on a binary tree, once you go down in the tree and you decide to either go left or right, then there's no reason ever to have to change your mind and to go backwards. Because if the number, if you went, for example, right, because the number you're looking for is bigger than the number that you're looking at, then you know it's got to be somewhere on the right. It can't be anywhere on the left. So, and that will hold true for the entire subtree. So, okay. Um, so Richard, do you have any questions about this so far?
No, not really.
Not really. Okay. So you understand the reason why you never need to change your mind. All right.
Yeah.
Okay. Now, again, focusing on the worst case. Um, if you're doing a binary search on a binary tree, um, in the worst case, what would happen?
The number you're looking for is the leaf.
Yeah, the number you're looking for is a leaf. Very good. In the worst case. So in the worst case, you're gonna go down to the quote unquote bottom of the tree or whatever the leaves are. Yeah, what you're looking for is a leaf. Okay. Um, Now, if there's, I'm going to try to keep you here, Richard. You're very correct there. That's right. That's the worst case. Worst case. Now, if this tree, right, like this entire tree, if it has n nodes, what's the depth of it?
If it had n nodes,
Yeah. So there's
it
n nodes in
would
the
be
entire tree, and I want to know how deep is it for a balanced tree.
on a balance tree.
Hmm.
Um, it's probably n divided by two.
Not quite right.
Not quite. No.
Well, let's see. So here's a tree on your left. That is a real tree. Is it balanced?
Yes.
Okay. I'll save you the time counting. There are 31 nodes in the tree on the left. Here, there's 31 nodes.
Mhm.
um, what's the depth of this tree? Like the actual number.
Um,
Like you can count.
it's four.
4, sure. All right. So you can call that 4. Um, 31 and 4. Not, can I call it 5? Because I want to include the 0. So
Zero.
the
Okay.
depth is 5, but if we're counting, we start at 0. Okay. 31 is not uh, or 5 is not 31 divided by 2. There's a different
Mm-hmm.
relationship. So um, how do you relate? Let me call it 32. 32 and 5. That's a bit easier. Let me ask you a different question. Um, how many nodes are on the 0th level?
How many nodes? One.
Yeah, 1. And on the first level?
Two.
Okay. Third level?
Four.
Okay. And the next one?
8.
All right. And the next?
16.
16. So what's happening there? When every time you add a new level, um, how many more nodes are you adding?
Like wait. So like it's like it's going up exponentially by like like n plus one power of n plus one, right? Or
Sure.
like it's
Close enough. Close. Yeah. I mean n. Yeah, it's not n to the, or something to the n plus 1 is fine. It depends on if you're counting layers, starting with 0, or what your conventions are. I don't care about plus 1s, minus 1s. But it's an exponent.
Yeah, yeah.
So 32 is, I'm sorry, 2 to the 5th, which means that log 2 of 32 is 5. If we added another level to this tree, let me get rid of this. If we added another level to this tree, how many nodes would we be adding?
It would be 2 to the power of 5.
Okay,
So, what is that?
32.
32.
32, yeah. So if you double the number of nodes that are above you, then, okay, well, whatever, I don't want to go there. All right, so that is to say that, okay, so if you have n nodes, then the depth is going to be log n. So if we have 32 nodes, then that you can build a tree with 5 levels. And in 5 levels, you can pack in 32 nodes. Why 32? Because you put half of them on the bottom, 16, and then half of what you have above that is 8, and then 4, 2, 1, and now you're full, and you've used up all of your nodes. So a depth 5 tree is good enough for that. So in this tree, and give me like the actual number, the tree on the left here. In the worst case, how many steps will it take to find a number that I'm looking for?
4. Or like, it would be the.
4 or 5?
Yeah, yeah.
Yeah. Yeah. Yep. Good. That's the actual number. Why is that the actual number? Because you already said the worst case is when the number is a leaf. And the distance from the root down, 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 down to the leaf is the depth of the tree for a balanced tree. They're the same thing. Leaves are the distance from the root to a leaf is the same as the depth of the tree if the tree is balanced. Make sense?
Yep.
Okay, perfect. Now, um, okay, so sorry guys, I gotta get into something and have it move a little bit faster. But before I do, I want to make sure that nobody's completely lost. If you have questions about a tree or something like this, now is the time to ask, because I'm gonna throw some stuff at you and go a little bit more quickly. You're good. Okay. So let's do this. I'm gonna shut off my cam for this because I need more writing. All right. Oh, I didn't mean to close the chat. All right. So how do we store a binary balanced, actually it doesn't matter, a binary tree inside of an array? Okay, this is a strange question, a little bit maybe, because an array looks like that, a binary tree looks like this. They look very different, right? Even this thing on the left, that's a balanced binary tree. Here's on the left an array. And my question is, how do we do this? How do we have a binary tree with an array? I want to, that's on again. Okay, so here the question is, how do you take a binary tree and encode it inside of an array? I want all of the benefits of a tree, but I'm going to be using an array. So I'm going to be representing an array. I'm going to be representing with an array a binary tree. Okay, so now things are mixing up a little bit. These are two different data structures. An array and a binary tree are different data structures, but you can use an array to encode a binary tree. That is to say that actually, if you're a little bit clever, these are the same data structure. You cannot make an array with multiple rows. No. That would be called a matrix, and you can not do that with an array. You can encode a matrix inside of an array, and that's very similar to what I'm talking about now, taking a tree and encoding it inside of an array. But an array is very simple. I mean, it's just it's a one-dimensional thing of cells, and that's it. Okay? But these two things can be equivalent, right? One is not stronger than the other because you can take an array and you can put your binary tree inside of it. And then when you're using this array, you're thinking about the array like a binary tree. And I'll explain how all of that works now. So it's not a good question. Before I was I've talked about linear search, I've talked about binary search. It's not a good question talking about the data structure. Is a binary tree better than an array? Because they are the same. Let me give you a simple way of doing it. Okay, there's two ways, two options. Two choices. The first way. I'll do an array like this, a binary tree like this. Let's see. Whatever. Okay, I'll take this binary tree, and what I'm going to do is I'm going to store this, encode it in an array. Encode. I'll call this layer by layer. Okay, so this is going to be turning into an array, and what I mean by encoding it layer by layer is I'm going to break up my layers like this. I'm going to put the root at the beginning. All right, so that's layer 0. And then I'm going to put layer 1 here, layer 1, which would be the number 6 and the number 15. Now I'm going to put layer 2, 5, 7, 12, 16. All right. I'm going to stop. Maybe I'm hoping that example demonstrated the way that this would work, but I want to pause and ask. Because this is only the first choice. There's another one that's a bit more complicated. Somebody has to have a question about this. There's no way we have this many students and everybody following. Yeah.
Array is not sorted.
So it is sorted, actually. It's just sorted in a different way. So here, it's not sorted from smallest to biggest. Instead, it's sorted as layers of a binary tree. So you'll notice for any layer, if I look at this layer, the numbers are sorted for that layer. for this layer, the numbers are also sorted. And for this layer, the root's just one number, so it's already sorted. So each of these layers are sorted if you just look at the layer. And then in addition to that, I'm sorting the layers. So I put layer 0, I put the first layer in the beginning. I put the next layer after that. So all of the layers, each layer is in sorted order. And for every layer, that's also sorted. So this, you can't call it unsorted. It's just sorted in a different way. Does that make sense?
Yes.
I just had a quick question. Do we always insert the layers from like left to right? So like the 6 would go before the 15, the 5 before the 7, 12, 16.
Mm-hmm.
Okay.
Well, I mean, it has to be a valid binary tree. You can start with a binary tree and then you just encode it in this way. Take the first layer, put that at the beginning. Take the second layer, one after the other after that. Then the next layer, one after the other. I mean, just each, the first layer, the second layer, third layer, fourth layer, fifth layer. You just write them out, right? So here, that's the first layer, the second layer, and the third layer. You just write them in sorted order. Start at the first, and then you keep going down.
If 16 had a leaf, or a child or whatever, like
Yep.
at the end, we wouldn't leave any blank spaces in the array, right? We just add one number after 16.
No. That's a very, very good question. And that's the problem with this. Let's say that we wanted to add the number 17. Okay? So this is also a balanced binary tree. It's fine. Let me get rid of these. I'm going to clean up a little bit. Okay. Now we have a new number, 17. That's a new layer. We're going to encode it the exact same way. All right? Which means that here we have a new layer. Right? This is going to be layer 3. And this is going to have 1, 2, 3, 4, 5, 6, 7, 8 places, right? Here's a blank space for the 5, right? I mean, all of these are blank, right? These don't have children. So all of these are blank spaces. And then we have the number 17. So what we can do is to put null values here. Null, 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 null. 17. There you go. There it is. So that's the layer, right? This is layer 3. This one. Here. Right? Null, 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 null. This is the way that we're encoding the binary tree. Layer by layer. Okay? There's the first layer. You're going to have 1 there. Here you're going to have 2 numbers. Here you're going to have 4 numbers. Here you're going to have 8 numbers. I mean, well, even if it's not a number, you need 8 places. If there's no node there, you put a null. You put a null value. But that's the way that we're encoding it, okay? Layer by layer, in order, okay? In a long line. Layer 0, layer 1, layer 2, layer 3, layer 4, layer 5, and on. You can give me any binary tree you want, and I can represent it inside of an array in this way. Do we always insert layer from left to right? Let's say yes. Let's say yes. Technically, you could do it differently, but this is the easiest and probably the most reliable thing is yes. You start, you store the root at the beginning, and then you go from there. Why do we need this kind of array, and how do we use it? That is another excellent question. That's great. So, why? Okay, a binary tree is so much faster doing a search. Okay, or you can do a binary search on a binary tree very easily. It takes log n time, obviously, because the depth of the tree is only log n. And in the worst case, you have to start at the root, you dig all the way down in the tree until you hit the bottom of the tree, and that is of a depth log n for a balanced tree. So it's obvious where the log n comes from when you're doing a search on this type of data structure. So this type of data structure, the binary tree, is a way to realize the binary search. Okay, a binary tree is a data structure, a binary search is an algorithm, but you can use a binary tree you can do a binary search on a binary tree very easily, and it's easier to maintain than using an array. I'll get more into this the next class. I can see I'm running out of time, but I want to answer this question. Why, if a binary tree is better, and I'm trying to tell you that it is better, why do this big step of putting it as an array? What's the point? The point is that we're storing stuff on hardware, right? This is the real world. In the real world, this data is going to be on this hard drive, or this hard drive, or it's going to be stored in RAM, or a solid state, or this. And all of them, work like an array. You have to think about the way that these operate as an array. There's no binary trees or complicated stuff. No, it's this is the beginning. This is the beginning of the drive here, and then it's a big long chain until you reach the end of the drive, and all of your data is inside of this array. Okay, that's the way that hardware works. But if we're clever, like this way, then we can we have to use an array. Okay, we have to, because that's the way that it's actually going to be stored in the real world. Not on a whiteboard, it's not math. This is like real world. You can't, it is an array. So you have to use one. And so we're doing this to be able to have the benefits of a different kind of data structure, and we encode it as an array because that's the hardware that we're actually using. But don't worry, even though the hardware is an array, we have a binary tree, and we can do all the things that you can do on a binary tree. We can still do here. We didn't lose anything. Okay, so this is why we're trying to convert or to encode a binary tree in an array. It's because we have to. All right. You're right. So that's why we need this kind of array. And how do we use it? We use it for search. So you take all of your data, and on the hard drive and RAM, whatever, you have a bunch of data, and now you're organizing it. You spend a lot of time doing this. You waste time taking all of your data and organizing it very carefully. That takes a bunch of time up front, but once you have it, now your data is organized in a particular kind of way, and now it's really easy to search through. You can do your search really quick. Okay? That's what databases are doing. They take a large amount of data, they store it on physical devices in such a way that it's especially easy to search through. Okay? That's the whole thing we're talking about in this first part. So it is 11:41. That's the end of class. Like I said, I'm not going to hold anybody after. I'm not going to teach any new material, but I'm happy to cover anything if people want to hang around after. You can log out. Let me go ahead and stop this recording as well.
So, Professor, just